So people seem to like the earlier videos that I made, the quad trees and the other example videos. So I thought I'd do one more. And I know that because you've submitted assignment 1 and you have, I'm sure other stuff to do, but I'm sure you'd much rather just write some more programs in Racket. So let's get to it. Today we're going to talk about something called a Lindenmayer system or an L system. So the goal for this video is we'll discuss how grammars, in addition to being able to match expressions, can also be run in reverse to generate expressions. We'll implement functions to generate Lindenmayer systems from a grammar, and then we'll implement a simple GUI that will draw Lindenmayer systems pictorially. So we'll see that Lindenmayer systems describe self-similar structures. And so by the end of this video, we'll have a way of drawing structures that look like this, but also by using the arrow keys, I will be able to make the Lindenmayer system grow and decrease in size, but also I'll be able to change the parameters of the Lindenmayer system, such as the angle that certain parts of the self-similar structure are drawn in. Now I should say before we go any farther, if you're going to follow along by typing in stuff along with me, which I think is a great idea always, you'll need to include these following libraries. So we'll need pict, which we used in quad trees, Racket draw, which is like a lower level drawing thing, and then this thing called universe, which we'll use at the very end for the GUI. We're also going to use the lazy lists that we implemented in lecture 11. So you're going to have to import lecture11.racket, but with this following provide directive, because we're going to want to use scons stream, scons take, scar, and scutter in our editor. So I will upload a new version of lecture 11 with this added, or you can just add it to a copy if you've got one locally. So we've had plenty of experience writing functions that operate on grammars, right? And all the functions that we've written that do that have taken a complex expression, like open paren, 1 plus 1, close paren, and have reduced it to a simpler one, right? So we have meanings for different operations, like in arithmetic language, and so we know ways of taking a complicated compound expression and making it a simpler one, such as 1 plus 1 reduces to 2. And we know that this is what interpreting an expression that satisfies a grammar is all about, right? The reason why we know that it's always going to generate a simpler expression is that we usually end up with more things on the right-hand side of a production than on the left-hand side, right? So in 1 plus 1, what we do is we say, well, if open paren 1 plus 1 close paren is parsed out correctly, then we know that it's an expression. And then if we know we have an expression, we have a program. So we've kind of gone from right to left, right? We take something complicated on the right-hand side, produce something simpler on the left-hand side, and we keep recursing up until we either have a valid program or a syntax error. But a question to ask is, what happens if we go in the other direction? Right, so today what we're going to use, we're going to use a different use of grammars. That is that when we interpret a grammar, we're actually going to build up a more complicated expression. So Lindenmayer was a biologist, and he was interested in studying mathematically the growth of biological systems like algae. So he came up with an L system for simulating the growth of algae. So what I'll do is I'm going to write the grammar first, and then we'll talk about what it means. All right? So we'll say that a symbol in this language, the language of expressions to simulate algae growth, is either going to be the symbol A or the symbol B. And we'll say that an expression is a list of one or more symbols. So I'm going to write that by saying it's either the list containing a symbol, or it's the cons of a symbol and an expression. Right? So in this language, we don't accept the empty list as a valid expression. The expression has to have one or more symbols. So I'm going to write some rules. So anytime we see an A, the right-hand side of that production is going to be the list containing the symbol A and the symbol B. right? So remember that this is the same thing as list symbol A, symbol B, but for simplicity, I'm going to write it like that. And a B is the list containing symbol A. So when we've dealt with grammars in the past, the way we've approached dealing with grammars is to say, well, anytime I see the list containing symbol A and symbol B, we reduce it from the right-hand side to the left-hand side. Here we're going to take the opposite approach. We're going to read these production rules from left to right. So what this means is anytime we see an A, we're going to replace that symbol A with the list containing A, B. So let's write a program that does that. I'm going to write a function called, we'll write define match iter algae. And it takes a symbol. The symbol will either be symbol A or symbol B. And let me write a signature for it here, why don't I? So this is going to take a symbol, and it's going to produce a list of symbol, right? Because one of the consequences of reading the grammar left to right is that we may consume a symbol, like A, but we may produce more than one symbol as a result. So you can kind of see intuitively how this kind of matches growth of algae, right? Like as we call iter algae more and more times, our petri dish of symbols is going to be growing too, right? So what we're going to do is we're going to say, well, if it's the symbol A, I'm just going to read it straight off from the grammar here, right? It's going to be the list containing A and B. And similarly, if S is B, it's just going to be the list containing A. So remember, because we're always returning a list of symbols, even if we are only taking in one symbol and producing one symbol, we don't produce a symbol, we produce a list of one symbol. So why don't we give this a try, see if it does the right thing. Okay, so if I call iter algae with symbol A, I get A, B, good. And if I call iter algae B, I get a symbol containing A. Okay, fantastic. So we've seen how to operate on one symbol, but remember that we are producing potentially multiple symbols as the output of iter algae. Right? So a thing that we would like to do is to say, well, transform every element in some list according to the function iter algae. And you might say, I know a function, a higher order function in particular, that will take a function and a list of things and apply that function to every element in the thing, right? We know it's map. So why don't we try map iter algae? And just as an example, why don't we do the list containing symbols A, B, and A? So this isn't quite what we want, right? Because we've only talked about lists of symbols. We've never talked about lists of symbols. And so you could imagine that this sort of nested structure is not really what we're looking for. So a thing that we would really like to do is, in addition to applying iter algae to each of these elements, we would also like to append all these sublists together into one. And you may be thinking, I know of a function that does just that. I remember it from my favorite quiz. The higher order function that we want here is conmapinate from quiz 1. Now in Racket, it's not called conmapinate. It has a less silly name. It's called append map. So iter algae. It does exactly what conmapinate did in the quiz, right? It applies the function, which takes, an A to a list of A, and then takes all the sublists and appends them all together into one list. So to give you a little bit of intuition for how our virtual petri dish grows, let's call append map with iter algae, starting with something simple, right? So we can call, actually we can even start somewhere simpler. We can start with the list containing B, and so we get A, and I'm going to keep manually just taking the output from append map and passing it back into append map like this. Just so we can kind of see how this grows. And then as it happens, there's an ABA. ABA. So that's all very fine and well. We can keep copying and pasting output into input until the cows come home. But it would be nice if we had a way of generating these things for us automatically. And in particular, a thing that might be nice to have is a way to generate not just one iteration of the algae, but rather a list of all the iterations of the algae, right? So the thing we would like to have is something like the list containing B, A, B, and then A, B, and so on. Now, there's a problem here, right? Because when we ran our grammars in the traditional direction, we always end up with some sort of base case, right? So we know when computation can terminate, right? We terminate when there's no simpler expression to evaluate. But here we have a problem, right? We're going in the opposite direction. Every time we call iter algae, we're creating larger and larger expressions, and that'll always continue, until the end of time, right? So this suggests that a way to express this is using a lazy list. So let's do that. So let's remind ourselves of how a lazy list or a stream works, right? So a stream containing things of type A, which in this case for us will be a list of symbols. It's either empty or it's scons of a thunk that's going to produce an A, a type A, which is going to be for us, remember, list of symbols. And XS is going to be a thunk that produces the next generation of our algae. Okay, so let's start writing a function called L system. Probably pretty important for a thing that generates L systems. It's going to take two arguments. It's going to take rules, which is a function from symbol to a list of symbol. And it's also going to take, I'm going to say start. So what start is, it's the initial state of our virtual petri dish, right? Which is a list of symbol. And what this is going to do, this is going to produce a stream of list of symbol. So we know that because it produces a stream of something, seems like scons is going to be a thing that we would need. So in order to figure out what to fill in next, let's imagine what we would like L system to produce, right? So recalling that when we call iter algae on AB to produce ABA, a thing that we would like is if we called L system with our rules function, which is iter algae. And let's say this is our starting universe, our starting petri dish. Right? The thing that we want it to produce here is probably scons of our initial petri dish, right? Which is A, B. And then if we evaluate the excess, the second argument, the thing that we want is a thing that produces scons whose first value is A, B, is the list A, B, A. Right? So that gives us a sense of how to proceed here, right? So if this call, the first thing that scons should produce is AB, well, in that case, it's just going to be start. Now, the more interesting case comes from what we said here, right? Where we want a thing that produces scons whose first value is ABA. So it seems like what that actually is an L system with the same rule set as what we were given, but whose start value is not the one we were given, but the output of append map. So let's do append map rules start. So let's see if this works, right? So I'm going to call scons take, which remember takes a scons and a num, and it will produce, basically it will materialize num number of elements out of the infinite list, right? So let's take 5 elements of L system iter LG. Now let's say our starting universe is just the list containing the symbol B. So let's see what we get. All right. So the first element is B. Second element is iter algae applied to B, which is A. Third is iter algae applied to A, which is AB, and so on. Okay, here's a different grammar. So this is what we call the Koch curve. The grammar is as follows. The symbol is going to be either F, or the symbol plus, or the symbol minus. And an expr is kind of what we said before. It's either going to be cons, or I guess list symbol, or cons symbol expr. The rules for the Koch curve are as follows. An F is going to get replaced with this list. It's going to be F plus F minus F minus F plus F. So that's a thing. And that's the only interesting one. If we have plus, we kind of leave it on its own. And same with minus. Okay, so let's write the same thing that we did for iter algae, but for iter Koch. So define match iter Koch, iter Koch s. So this is a function that takes a symbol, produces a list of symbol, just like the other one. And once again, we can kind of just read things off from the grammar up here. Right? So if it's F, it's going to be F plus F minus F minus F plus F. And then symbol plus, symbol minus, list containing minus. Okay. So let's just convince ourselves that this does the right thing. It's printing out. I guess we don't need to have that printed out over and over again. If I call iter Koch with F, we get that interesting thing. If I call iter Koch with just plus, okay, and iter Koch minus, okay. So let's talk about what each of these symbols means in the context of actually drawing the Koch curve. So this is a visual thing. It's in fact, it's the self-similar structure that we saw at the beginning of the video. And the way to think about this is, you can think of these as commands if you're a pen moving around on a sheet of paper. All right, so a pen has a certain position on the page, and let's say it's facing at a certain angle, right? So if you see an F, what that means is the pen should move forward. If you see a plus, it means the pen's going to rotate 90 degrees, so it can move forward in a different direction. And minus means the same thing, except it's going to rotate 90 degrees the other way. Okay. So If we want to draw the output of this grammar pictorially, we need to set up some stuff in Racket to make this happen, right? So we've talked about this pen, it's got an XY position, it's got angles, it's got stuff like that. So let's write a structure that's going to hold all these pieces of information together. So I'm going to define a structure, struct, I'm going to call it state, and it's got the X and the Y and the angle theta. I'm also going to have it store step len, so that's when we go forward. It's going to know how many pixels to actually move forward. And I'm actually going to say angle size. I don't really know what to call that, but that's the idea of when we turn left and right. I said 90 degrees here, but maybe we don't want it to be 90 degrees. Maybe we would like to vary what that angle is. And the angle that we rotate when we go left or right is going to be stored in angle size here. And like always, I'm going to do #transparent so that we can actually see what the values of the state are if we evaluate a state like in the REPL. Okay. So we said the two things that we can do with the state is to move the pen in some direction and to rotate the pen. Right? So it seems like we want to write functions that'll do that for us. So I'm going to say define state move, state move, which will take a state and a number and produce another state. And so we're going to have a state and then a distance. So what's this going to do? So what this is going to do is we have a point, some xy point, and an angle, and it's going to move that point distance units in the theta direction. So this just requires a little bit of trig. So what I'm going to do is I'm going to say let x0 to be state x of s. So I'm extracting out x out of the state. Pardon me. And let's do the same thing with y0, state y of x. Let's grab theta as well. I find that even though this expression isn't that much more complicated than this, it's nice to bind names to things, because otherwise the expression that consumes x0, y0, and theta can be a little hairy to read if there's too many parens. So I'm just extracting these things out just to make the final expression a little simpler. That's all. So the more interesting one is going to be x1, right? So we're going to add to x0. We want to take the cos of theta. We're going to multiply that by the distance we want to travel. And we're going to do the same thing for y, except for cos it'll be sine. And the thing we're going to do is now produce a new state. So we're going to produce the state whose new y position is, oops, that should be y1, but whose new x position should be x1, whose new y position is y1. We didn't change theta, so theta remains the same. We didn't change the step length, so I guess I could have extracted step length here as well. I didn't, but you can if you want. State step len s and state angle size s. And that's the function that moves us in some particular direction. So why don't we see if it does the right thing? I'm going to define a default state for us. So this is going to be the state at position x0, y10. So it's just down a little bit, but on the left-hand side of the image. Let's say angle is 0. We'll do a default step length. Define default step length 10 pixels. Oh, I don't know. And then a default rotation angle will be 90 degrees. So the default step length will be that, and the default rotation angle will be that. Make sure everything runs as it should. So if I run state move default state, whoops, and let's say we want to move 10 pixels, right? So the default theta is 0, so we're going to move in 10 pixels. So if we've done everything here correctly, what this should produce is state 10, because theta is 0. Y remains the same, everything else remains the same. So let's see if that works. We got 10 and 0. Oh, yeah, I screwed that up. That should be Y0. So it's a good thing we did that test. Let me run it once more. We should see 10, 10 for the position, and everything else remains the same. And that's what we see. So the other thing we want to do is rotate, right? So let's do the rotation. The rotation is a lot easier. We don't have to do any trig stuff. That's all handled in state move. So this will take a state and a number and produce another state. So we'll do define state rotate S and angle, I guess. And we can call it theta. Be consistent here. So it's going to be the state containing the x value of S, the y value of S. We're going to add theta to state theta of S. And then it will be the same as this stuff here. So I'll just copy and paste those fields out like that. So if we do a state rotate of pi over 2, say, so we'll do state rotate default state over pi 2. What we should see is we're still at 0, 10, but now theta has changed. 0, 10, theta has changed. Okay, so these are the rules for drawing the co-curve that we mentioned just before. So let's write a function that takes in, I'm going to call it next state. It's going to take in a symbol, and it's going to take in a state. So this is going to be a function that takes a symbol, state, and it's going to produce a new state. And the state it's going to produce is going to be dependent on the symbol that we got and these rules here. So let's match the symbol. If it's an F, what do we want to do? We want to walk forward, right? So we're going to state move, I'm going to call that S. Because state is a keyword, it's not a keyword, but it's the constructor for state up here. So I don't want it, we won't be creating any new states in this function here, but I don't want to shadow that identifier. So I'm going to call it S. So we state move S. How much do we want to move forward by? Well, we want to move forward by the step length in S. So that's state step len of S. One more. If we see a plus, what are we going to do? We're going to rotate, right? So we're going to state rotate S, state angle size. And we're going to do the same thing with minus. The difference is that we're going to make it negative. So slightly annoying to do. We subtract in that way, so we get the negation, and then that's our function. Should we, step len, see if that's any better. So why don't we give it a try? Let's do next state, where you get go forward with default state. So we start at 0, 10. We have a step length of 10. So this should be just what we did earlier, right? We should get 10, 10. Now something that's probably worth doing is let's bind a co-curve to an identifier. So I'm just going to call KC. to be, so we're going to scons take L system defined by iter koch, starting with just move forward. And let's grab the fourth one. Just for now, we can always change this later. But remember, this returns the list. This returns all the generations up to generation 4. Let's say we're only interested in the last one. So this will extract the last element out of that list of lists. So if we print out what KC is down here in the REPL, we'll see it's a reasonably complicated co-curve expression here. I wonder how long it is. Let's do len KC, length KC. So it's 249 steps to take when we call this, when we operate over this co-curve, which is kind of wild if you think about it. Right? We only started with one step in the initial version, and then by generation 4 we have 249. Now you might be saying to yourself, well, I recognize the type signature that looks like this. This is from an A to a B to a B. So we know a higher order function that operates on types A and B with a function that goes from an A to a B to a B. That's a fold, right? So if we fold over next state, starting with default state, and let's give it the co-curve that we've saved up here. Remember, we did that. Oh, we did it right here, right? So it's the 4th generation of the co-curve. We should get back a state, right? So this is the final state after having performed all these operations on the co-curve. Now you might be thinking to yourself, well, that seems kind of funny, right? It's not necessarily clear how that computation happened. So let's introduce something that I probably should have talked about before, which is require Racket trace. And what Racket trace is going to do is it lets us annotate a particular function to say every time a function is called, print out in the REPL the arguments that were passed to it and the value that's produced. So if I do trace next state, and I do fold our next state, default state with KC. So this is just the same expression that we ran a minute ago. We'll be able to see all the calls to next state as more and more elements are from KC are passed into next state. Right? So we can kind of see here that the trend for the co-curve is to kind of move from left to right, and we've kind of gone down a little bit, so we have a greater Y parameter. We can see that we're moving left and right with 90-degree increments, and we've kind of gone down, and now the Y-axis is decreasing, so we're kind of going back up towards the top of the image. So that's kind of nice, I guess. It kind of gives us a little bit of intuition for what's going on here. Just to demonstrate, with F and the state in this position, we can see that the theta is 0, so we know that we should be moving 10 units rightward, and you can see that we do indeed move as the ultimate step from 260 to 270 for our Y parameter, for our X parameter. So that's cool, but I think it's a lot cooler to see this pictorially, if we can actually draw it out. So let's do that. So let's write a meaty function here. Let me say define draw. What should we call it? Draw. We'll call it draw coke for now. I think it's actually going to be more general than that, so we can rename it a little bit later. So what it's going to take is it's going to take a list of symbols. Right, so this is going to be a function that consumes list of symbol and produces image. And so what I've done is here, because I've imported Racket draw, inside draw coke, I'm going to define these things here. You haven't seen these before. I had to look up how to do this in Racket. So there's no reason for this to be anything other than completely opaque. So I'm going to define something called a target, which is make bitmap. Oh, we need a width and height, which we didn't define. So let's do define state width, I don't know, 800, state, define state height, 600. We can change these later. But the image that's going to be returned is of dimensions state width and state height. We're also going to define this other thing, define DC. So this is actually your first instance of an object in Racket. So we're now using Racket's actual object system, not the one that we invented in lecture. So it's a new instance of a bitmap DC whose bitmap target is going to be the target we defined. So this is all super opaque. The point is that target is the image that's going to be returned at the end of whatever we do inside drawCog. Right? So a bunch of stuff is going to happen, and then we're going to return target. That's basically how it's going to look. Okay. So we need, in order to draw things on the target, we need a function that's going to behave very similarly to nextState, but we may need to also draw things on the target if we need to draw a line. So the idea is that when we walk forward, when we change state from some position to some other position, we're going to draw a line there. And at the end of the day, what we'll see is the entire code curve that's been drawn once we've exhausted all the symbols that we've been given. Okay, so I'm going to write a function called define draw symbol, I don't know, and it's going to take a symbol and the current state of the world, which will be, so this is a symbol to state to state. So this will produce our new state. All right. So what I'm going to do is I'm going to call our next state function up here. Call it S2. I don't know. Right. So we're going to call next state with symbol and the S. I just want to make sure so symbol state state. And I'm going to write a form that you've not seen before, something called begin. So what begin is it has any number of expressions. What this evaluates to is whatever the last expression is, but we can have side effects or mutability inside our begin block. Well, we can have mutability anywhere here, but the point of having begin at all is that everything that isn't the last expression is something that's going to have a side effect. And you should feel itchy about this, given that we've said mutability is bad, side effects are bad, pure functions are good. So let me just write it and we'll talk about it. We'll have a conversation. So what I'm going to do is I'm going to do send DC. This is how Racket sends messages in its object system. So we're sending to DC, this thing here, the command draw line. And the things draw line has 4 arguments: the initial x, the initial y, the new x, and the new y. So it's going to be it's going to be state x of s, state y of s, state x of s2, state y of s2. And at the end, we want to return new state. So this is very similar to what nextState does in the sense that, well, we call nextState. So basically, the only difference between what we've written here and up here is it produces the same thing that nextState does, but at every step, it's going to have this side effecting operation that draws the line onto our bitmap target. So that shouldn't surprise you to learn that the thing that we're going to have here is we're going to fold in exactly the same way we did before when we were printing all the stuff down here. But we're going to fold over draw symbol, starting with default state and sims. I don't know why I put the B there. I don't know. Doesn't have to be there. Doesn't have to be there. Sims. But remember that we want to have it return an image, right? So in particular, we're going to have a begin block where we write the whole thing onto the target, and then we return the target. So let's see if that is okay syntactically. Oh, I called it S2. Yeah. It's taking its sweet time. My laptop's almost a decade old, so you know it's a little slow. Why don't we try it? Why don't we see what this does? So we're going to call draw Coke with KC. It's chugging along. And at the top of the screen here, what we see is our first Coke curve. Okay, so we should talk about the elephant in the room here, which is that we are using mutable variables inside our function draw Coke here, right? So your feeling might be that this isn't necessarily great, but there's a good lesson to take from this here, which is, you know, we spend all this time talking about how mutability is bad because if you mutate things outside scopes, all this sort of stuff, you lose referential transparency, and that's bad, and it's hard to reason about. But notice that what we've done here, we live in the real world. This is a library that we've used, that we've imported from Racket, that we didn't have control over. We didn't design this. It's designed to have mutable identifiers in it, and that's how it's intended to be used. So what we've done is we've limited the mutability by saying, okay, we concede that we have to do these things where we send draw line to an object. Fine, we have to do that because this was code that was given to us. But we've isolated all the mutability inside this function, right? So even though there are side effecting operations inside draw Coke itself is not, still preserves referential transparency, because the only thing that gets mutated sorry, let me try that again. The only thing that gets mutated is DC and therefore target. And those are things that have been created inside draw Coke. So kind of what we've done is we've created this firewall of mutability around draw Coke. So even though we require mutability here, draw Coke is itself still referentially transparent. So this is a good thing to do when you're dealing with other people's code, you're using libraries, when you're out in the real world. You might say, okay, well, I would like this to be, you know, a nice immutable function, but the libraries that I'm using are mutable. Well, one way to get around that is to limit the amount of mutability that you're doing such that anyone that calls your functions, in particular, anyone that calls draw Coke, they don't know if there's mutable state going on inside the function because you've isolated it, right? It's all contained within the function itself. That's a useful thing to keep in mind when you're implementing more complex things, when you go out into industry, working on real world code and so on. Okay, so the last thing we're going to do today is create the interactive GUI. And this actually won't take very long because Racket has a really nice GUI framework called Universe. So the first thing we're going to write is a function that handles key presses in our GUI. So I'm going to say define, I'm going to call it handle key. And this is a function that's going to take our state and a key and produce a new state. Define handle key, we'll call it S and K maybe. So cond there are four things that we can do in our GUI, right? We can either make the co-curve smaller, we can make it bigger, we can make the angle smaller, we can make the angle bigger, right? So what I'm going to do is I'm going to say, is the key equal to the left arrow key? If it is, we're going to produce a new state where the only difference is the angle is slightly smaller. Right? So it's going to be state X, S, state Y, S, if I can type, state theta, S, state step len, S, and state angle size N. I'm just going to copy this because I'm going to have to rewrite something pretty similar. So the only difference here is that we want our angle to be slightly lower. So let's do that. We can say, we'll do the same thing for, I'm going to paste that down there. We'll do the same thing for the right arrow. The difference is we're going to add slightly. Right? So if we hit the left arrow, we're going to decrease the angle slightly. If we hit the right arrow, it's going to increase the angle slightly. And now we'll do the same thing for the step length. So key K up. So if we hit the up key, let's increase the step size by 1. And then we'll do the same thing for down, which will decrease the step size by 1. Okay. So that's kind of a lengthy function there, but it's mostly all redundant. We're just taking in a state and a key press, and we modify a particular aspect of the current state based on which key it was. Okay. The slightly more interesting thing is going to be function, whoops, I'm writing rake here. I don't know why I called it function. Define, I'm going to call it render state. So in computer graphics, to render an image is to take some data structure and to make a picture out of it. So render state is going to look pretty similar to what we had before. In fact, we called a function that did that pretty nicely. Right? So what this is going to be is that this is going to be render state, which is going to be draw coq. And draw coq takes, oh, there's one thing we need to do here. Actually, is that the only thing we need to do? No, it isn't. So right now we're hard coding the initial state, but remember with key presses our initial state may change. So I'm going to call this initial state, and we'll do initial state to an image, right? So then this will be draw coq. I've already forgotten. Oh yeah, so this will be KC. We'll leave that as a constant. We're always going to draw some variation on this particular co-curve here with state. In fact, I guess this could even be, we could write it as a query if we wanted to. And the thing that ties it all together is this thing called Big Bang. It's Big Bang because it creates a universe. It's a metaphor they really run with. So Big Bang, our initial state is going to be the default state. And to draw, basically what this is saying that when we want to draw something, it's going to call a function, and it's going to call our render function. And on key is the function that gets called when a key button gets pressed. Again, I just looked this up from the Racket documentation. You're not expected to know this. I'm not expected to know this. I just looked up the documentation. It's called handle key. Okay, so I made some typos, which I then copied and pasted. So let's fix those quickly. State -y. And we need to close those, which means we had one too many parens on that side. Okay, so now let's see if it works. So this is what I see on my screen. So the render function is clearly working. If I hit up, you can see that the key handler is being called and it's getting larger. If I hit left, what we see is that the angle that we're drawing the curve with is getting larger, and so the shape changes, right? And I can do the opposite by hitting right and down respectively. So before we do the last thing for this video, let's sum up what we did. So we created an interactive GUI using Big Bang that renders and handles key input. It handles key input and renders things based on this notion of state, which was an X and Y, an angle position of a pen on a piece of paper. We got those positions from computing all the different operations that we need to do to move that pen at different points on our little piece of paper. And we got those from generating a list of symbols from a grammar. We generated a list of grammar. We generated several generations of an else system according to these rules here. So it seems like the only thing that is really dependent on the Koch curve here in particular is iter Koch. And see, in fact, you can even see that we only have one binding to iter Koch here, which is to KC. All right, we grabbed the last generation. Where did KC go? It's right here. Right? So we grabbed the final iteration out of a bunch of iterations of iter Koch, and we just passed that into our GUI handler. So it seems like the only thing that we need to change if we want to draw a new kind of else system is to change what else system grammar generator function gets passed into else system. So why don't we end this up just by changing the else system just with one more definition of an else system, and we'll just see everything just work automatically. The dragon curve is defined like this. It has forward, plus and minus, just like the Koch curve does, but it has two more symbols, x and y. The idea is that anytime you see an x, it expands to these more complicated symbols, and everything else always just remains the same. So subsequent iterations of the dragon curve, if you see an x, that part becomes more complicated, and y, that part becomes more complicated. But if you see an f, it'll just remain an f. So it's different from the Koch curve up here, where the thing that changed from one generation to a next is that f expanded into a more complicated. Let's write the equivalent of iter Koch for the dragon curve. So we'll call it define match iter dragon s. And we're just going to do the same thing that we did with Koch curve, right? So we'll say if we have x, this will produce the list x plus y f plus, and I'm just reading it off the grammar here, just like we did before. Same thing with y. It's going to be minus fx minus y. Because all the other symbols, well, no, let's write it explicitly, actually. So at this point, we'll just do this. Do this. So with f produces the list just containing f, same with plus and minus. There is one more thing that I do want to change here, which is in next state. If we encounter a symbol that doesn't mean a move or a rotate, so for instance, x and y up here exist only to expand the list of symbols, they don't actually indicate what the pen should do. Well, here we would throw an error, right? Because we're not matching symbol with any other case. So a thing that I would like to do here is just to say, if it matches anything else, just produce the symbol. Just produce the state that we started with. And so I'm going to call define drag, and it's going to be all of this. with a few things changed. So we're going to generate the L system, not from the co-curve, but iter dragon. I think I called it iter dragon. I did. Iter dragon. So we're going to use this set of rules. We're going to start things off with the initial generation being f and x. The co-curve grows more quickly than the dragon curve, so let's use the 11th generation of the dragon curve. So let's ignore this for a second. This was me just sort of playing around with things. So when we render state, we're going to want to render drag. And if we run Big Bang again, we can zoom out a little bit and see slightly more of it. It actually grows rather large. Another thing that I did do that I didn't put in the video is that I changed the starting state to not be 0, 10, but the center of the world, just because the dragon curve grows out differently than the co-curve. Right, so that's what the co-curve looks like. And just as before, I can use the left and right arrow keys to change the angle that's used when plus and minus are evaluated. So that's all I got. Hopefully that was interesting or informative, hopefully both. If you have questions, obviously come to my office hours, shoot me an email. Hit the subscribe button and mash the bell. I think that's what I'm supposed to say at the end of these. So enjoy the rest of your break and see you for Lab 5 on following Monday. Okay.